Installing three 208 volts, single-phase heat pumps, each rated at 5.2 amps, on a single 20 amps branch circuit is not permissible. The decision hinges on the fundamental principles of electrical load calculation and adherence to the National Electrical Code, or NEC. Let's delve into the reasons why this configuration is non-compliant and explore the underlying electrical concepts. Firstly, consider the total load imposed by the heat pumps and the circuit. With each heat pump drawing 5.2 amps, the cumulative load for 3 units is 15.6 amps. While this value appears to be within the 20 amp circuit capacity, the NEC mandates specific deterring factors and overcurrent protection requirements, especially for continuous loads. Secondly, the NEC defines a continuous load as one where the maximum current is expected to continue for 3 hours or more. Heat pumps, by their operational nature, often run for extended periods, thus qualifying as continuous loads. For continuous loads, the NEC requires that the branch circuit be rated for no less than 125% of the continuous load. In this scenario, the continuous load is 15.6 amps. Multiplying this by 1.25 yields a required circuit capacity of 19.5 amps. While 19.5 amps is still technically below the 20 amps rating of the branch circuit, it leaves a very minimal margin and does not account for any other potential loads on the circuit. Furthermore, it's essential to consider the inrush current of the heat pumps. When a heat pump motor starts, it draws a significantly higher current than its rated running current. This inrush current, even for a brief period, can overload the circuit and potentially trip the circuit breaker. The 15 amps fuses at each heat pump unit serve to protect the individual units from internal faults and overcurrent conditions. However, they do not negate the requirement for proper branch circuit sizing and overcurrent protection. The branch circuit breaker must be adequately sized to handle the total continuous load, inrush current, and any other potential loads on the circuit. Thirdly, the NEC provides specific guidelines for sizing branch circuits that supply motor-operated appliances such as heat pumps. These guidelines are outlined in Article 440 of the NEC, which covers air conditioning and refrigeration equipment. Article 440 addresses the requirements for conductors, overcurrent protection, and disconnecting means for such equipment. The NEC specifies that the branch circuit conductors must have an ampacity not less than 125% of the equipment's rated load current. In this case, each heat pump has a rated load current of 5.2 amps. Therefore, the branch circuit conductors serving each heat pump must have an ampacity of at least 6.5 amps per heat pump. When multiple heat pumps are connected to a single branch circuit, the conductor ampacity must be sufficient to handle the sum of these individual requirements. The NEC also addresses the sizing of the branch circuit overcurrent protection. The overcurrent protection device, typically a circuit breaker or fuse, must be capable of handling the starting current of the heat pumps while still providing protection against overloads and short circuits. The NEC allows for specific overcurrent protection ratings based on the type of motor and the equipment's design. It's crucial to consult Article 440 and the equipment's nameplate data to determine the appropriate overcurrent protection rating. Fourthly, consider voltage drop. With 3 heat pumps operating on a single 20 amp circuit, the potential for voltage drop increases significantly. Voltage drop occurs when the voltage at the load end of the circuit is lower than the voltage at the source end due to the impedance of the conductors. Excessive voltage drop can lead to inefficient operation of the heat pumps, reduced performance, and potential equipment damage. The NEC recommends limiting voltage drop on branch circuits to no more than 3%. To minimize voltage drop, it's often necessary to increase the conductor size. The appropriate conductor size depends on the length of the circuit, the load current, and the allowable voltage drop. Using a voltage drop calculator can help determine the optimal conductor size for the specific installation. Fifthly, the physical limitations of the circuit breaker panel must be considered. A standard 20 amp single pole circuit breaker occupies 1 slot in the panel. Installing 3 separate 20 amp circuits, one for each heat pump, would require 3 available slots in the panel. If the panel is already fully populated or has limited space, it may not be possible to add the necessary circuit breakers. In such cases, it may be necessary to upgrade the panel or install a subpanel to accommodate the additional circuits. Sixthly, the potential for nuisance tripping of the circuit breaker must be considered. If the circuit breaker is too close to its maximum rated capacity, even minor fluctuations in the load current or temporary overloads can cause it to trip. This can be particularly problematic during periods of high demand or when multiple appliances are operating simultaneously on the same circuit. To avoid nuisance tripping, it's generally recommended to size the circuit breaker with some margin of safety. This means selecting a circuit breaker with a slightly higher ampacity in the calculated load current. Seventhly, the specific requirements of the local electrical code must be considered. While the NEC provides a comprehensive set of guidelines, local jurisdictions may have additional or more stringent requirements. It's essential to consult with the local electrical inspector or authority having jurisdiction to ensure compliance with all applicable codes and regulations. The AHJ can provide clarification on any specific requirements or interpretations that may apply to the installation. Eighthly, the manufacturer's recommendations for the heat pumps must be followed. The manufacturer's installation instructions typically specify the recommended circuit size, overcurrent protection, and wiring requirements for the equipment. These recommendations are based on the equipment's design and performance characteristics. Deviating from the manufacturer's recommendations can void the warranty and potentially lead to equipment damage or safety hazards. Ninthly, the importance of proper grounding and bonding must be emphasized. Grounding and bonding are essential for electrical safety and help to prevent electric shock hazards. The grounding system provides a low impedance path for fault currents to return to the source, allowing the overcurrent protection device to trip and energize the circuit. Bonding ensures that all metallic parts of the electrical system are electrically connected, minimizing the potential for voltage differences and shock hazards. The NEC provides detailed requirements for grounding and bonding in Article 250. These requirements must be strictly followed to ensure a safe and reliable electrical installation. Tenthly, the potential for future expansion or changes in load must be considered. If there is a possibility that additional electrical loads will be added to the circuit in the future, it's wise to plan accordingly. This may involve oversizing the circuit conductors and overcurrent protection to accommodate the anticipated future loads. It's also important to consider the capacity of the electrical panel and ensure that it has sufficient space for additional circuit breakers. Planning for future expansion can help avoid costly and disruptive upgrades later on. In summary, connecting three 208 volts single-phase heat pumps, each rated at 5.2 amps to a single 20 amps branch circuit is not permissible due to NEC requirements for continuous loads, overcurrent protection, voltage drop, and potential for nuisance tripping. Each heat pump should have its own dedicated circuit that meets the NEC guidelines and manufacturer's recommendations. Always consult with a qualified electrician to ensure that all electrical work is performed safely and in accordance with applicable codes and regulations.